Hi, in this presentation we'll be going over the different classifications and applications of robotic exoskeletons, a subclass of wearable robotics. My name is Luke Majet, and with my colleague Dulcinea Carroll, we look forward to teaching you today. Wearable robots are a subclass of the large field known as robotics. Robotics encompasses everything you think about with robots, from shipping drones to military advancements, or this Atlas robot pictured here. Within that large field, wearable robotics deals specifically with robots that are made to be contoured by the human body and operate with them, like this Honda walking assistance device for mobility and comfort. Within wearable robotics, the further classes are robotic exoskeletons and prosthetic robots. Robotic exoskeletons cover and add to an existing part of the body, usually to strengthen an injured limb or expand human capacity. Prosthetics, on the other hand, aim to replace a limb that is missing entirely. An important definition is that robotic exoskeletons are active mechanical devices that are essentially anthropomorphic in nature. They are worn by an operator and fit closely to his or her body and work in concert with the operator's movements.
What is the purpose of wearable robots? Why do we use them? Wearable robotics nowadays are used in many fields, from in factories to hospitals to even in the home. They have been used to improve worker safety with injury prevention and increase worker productivity and endurance. Medically, they can be used to help in physical therapy with rehabilitation and increased movement for people with mobility impairments or paralysis. In the photos, we can see some examples from the medical, military, and industrial fields. Exoskeletons and wearable technology began with mainly medical purposes, both training and assistive. They then expanded more into military usage and then industrial and commercial, making this technology even more accessible. Exoskeletons versus prosthesis. Both are examples of wearable technology. They have key differences in form and function. The exoskeleton has two main purposes: empowering and orthotic. Empowering exoskeletons are used to increase the user's strength and endurance. They are modeled on the wearer's body. It has been used in the military to allow soldiers to travel long distances while carrying gear. They take the weight from the pack and redistribute the pressure to the ground or a lower impact part of the body. Empowering exoskeletons extend stamina and reduce fatigue for the user. Meanwhile, the orthotic exoskeletons are designed to assist in motion as a mobility aid or restrict motion as a form of physical therapy and rehab to train the wearer. This is modeled after the wearer's limb or body part. Orthotic exoskeletons can be used to assist the elderly or those suffering from a stroke or spinal cord injury in increasing movement. Prosthesis, rather than assist a body part, is designed to replace a body part. Prosthetics are helpful for people who have lost a limb. People can be born with limb loss, have a limb amputated, or have a severe injury to a limb. When you think of exoskeletons, you may think of a superhero you know and love, Iron Man. A more realistic example is the Raytheon XOS-2 exoskeleton. It has been called the real Iron Man suit because of how it can enhance the wearer's strength and endurance, reminiscent of Tony Stark's suit.
Now that we have a general grasp of what exoskeletons and prosthetics are, we'll go over the different classes of exoskeletons. There are many types of categories each exoskeleton can fall into, and these distinguishing features can help determine which exoskeletons serve which purposes. One of the most important classifications for exoskeletons is their application, or more broadly, the field that an exoskeleton is used in. Military exoskeletons are used to augment human ability and empower soldiers. Like in the bleaks shown here, the robotic muscles work in parallel with the human muscle, allowing the soldier to carry a very heavy load without fatigue. Industrial exoskeletons assist workers with bodily fatigue, and similar to military applications, can be used to augment human abilities to exceed natural limits. Consumer exoskeletons serve to improve human ability for sport and prevent injuries by supporting the human body during athletic endeavors. Medical exoskeletons can also be used for two large groups of applications, explicitly defined as training devices and mobility aid devices. Mobility aids assist patients who will never be able to achieve normal motor ability, and these suits serve to replicate human ability and assist these patients with independence. The common analogy for these devices is that a regular human muscle is a bike, these mobility aids are an electric bike, adding a motor to the existing ability to improve function. Trainer devices, on the other hand, rehabilitate patients who have experienced injury, such as a stroke or spinal cord injury, and assist those who have struggled with motor function. These devices are used by physical therapists and are permanent fixtures in hospitals, working with patients toward a goal of them no longer needing the assistance that this device provides. To return to the bike analogy, these trainer devices are likened to training wheels, which are temporarily added to a bike until the rider no longer needs them to ride. The next classification for exoskeletons is that by body segment. Lower body exoskeletons operate between the hip and the foot, spanning the other joints in between as well. Upper body exoskeletons operate between the neck and hip, also including the back and joints in the arms. Full body exoskeletons can come in many varieties, being active in a combination of any of these joints. An important concept when discussing exoskeletons, and particularly the classification of exoskeletons, is degrees of freedom, particularly those in your joints. The degrees of freedom of a joint is the minimum number of independent parameters needed to define a joint. When dealing with exoskeletons, relative degrees of freedom are the metric being measured, and they're often a metric for how complex a system is. The human body has different types of joints, just like exoskeletons, which can be classified by the degrees of freedom each has. Some of your joints only allow for 1 degree of freedom, such as your knee, which only moves about a single axis, known as flexion or extension. An example of a joint with 2 degrees of freedom is your elbow, which can be flexed but also can be twisted. Finally, a 3 degree of freedom joint would be the shoulder, which acts as a ball joint relative to the torso. It can flex and rotate in 2 different axes. Now that we know what degrees of freedom are, we can recontextualize them in the scope of exoskeletons. Like the joints on your body, different exoskeletons can be classified by the degrees of freedom each has. The example here with 1 degree of freedom is a project from the Stevens Wearable Robotic Systems Lab, which has its 1 degree of freedom at the joint between the foot and the ankle. The example with 2 degrees of freedom has those 2 degrees of freedom moving in the elbow, moving it straight and curved, and also twisting the forearm, just like the joint on your body. The 3 degree of freedom example has its 3 body segments at the hip, the knee, and the ankle.
Another classification is by whether an exoskeleton is a monoarticular or biarticular mechanism. Monoarticular means that there is one motor per joint, while biarticular means that the motor spans multiple joints. The monoarticular example is the exoboot. The exoboot only addresses one joint, the ankle. On the right is Harvard's soft exosuit. This suit has straps that reach from the hip to the ankle joint. It works with hip flexion and ankle plantar flexion. The load path passes directly through the knee joint, so there is no net torque exerted on the knee joint.
Another classification is by portability, which is broken into 2 main sections, fixed and portable. Fixed denotes an exoskeleton that is permanent and immobile, like that pictured at the bottom left. These structures are often used to rehabilitate patients after suffering a spinal cord injury or a stroke. Portable exoskeletons attach to the patient's body and keep attached to the patient as they go about their day, and are used for a wider variety of applications. The next classification for robotic exoskeletons is that by anchoring point, or the type of force exerted by the device. Internal force exoskeletons have anchoring points on the wearer's body and distribute forces across the body, as exemplified by the Darwing product below. The force on his lower back is redirected by the exoskeleton to ease back pain and improve endurance and weight capacity. In external force exoskeletons, the anchoring points are off of the wearer's body, often on a wall or ceiling mount. These devices redistribute the wearer's forces to the ground, like the Lacomat shown below. The patient's forces are grounded by the exoskeleton. Another classification for exoskeletons is their rigidity, which is broken into 2 categories. Soft exosuits, as the name implies, don't have any hard structure and are usually very close fit to the body of the wearer, like the Harvard shoulder exosuit pictured on the left. The device uses a fabric to attach to the body in a form-fitting fashion. Rigid exoskeletons, however, use hard mechanical structures to serve their intended purpose. As shown by the metal structures on the obliques, without these rigid structures, the device wouldn't be able to transfer heavy forces down the body.
Passive versus active joints. There are 3 variations in exoskeletons. The main difference is the usage of motors. Passive exoskeletons have no motors. They are mostly used for gravity counterbalance. These exoskeletons can be useful as support to prevent injuries from repetitive tasks or as help to hold tools. The image below shows an exoskeleton for workers that need to hold things like a drill up high for extended periods of time. The device redistributes the weight of the tool and the wearer's arms to a lower impact point of the body, The hips. Active exoskeletons have joints controlled by motors, though not every joint needs to be active to make an exoskeleton active. There can be a combination of passive and active elements. One of the many ways active exoskeletons are helpful is with lifting heavy objects and preventing injury. Semi-active exoskeletons have the primary action as passive, but use a motor and an elastic element, like a spring, to adjust the structure for the wearer. It can adjust the assistive or restrictive level, which can be helpful for rehabilitation uses. Thank you for listening. To hear about examples of exoskeletons and their classifications, watch part 2 of Powered Exoskeletons for Assistance and Rehabilitation.